ready, Ryan?
Yes.
Okay, go ahead.
So good afternoon, everyone. My name is Ryan, and today I'm going to talk about the concept about the partial derivatives, and which is the very important part in the multivariable calculus. And for today's content, I'm going to talk about why we need partial derivatives and what the concept means and how we define it formally. And in the end, I will give you a simple example. And so before I'm going to talk about that, I want to get a quick review. So for this diagram, it shows that the y equals to kx. And if we want to get the gradient of that, who can answer me? What's the gradient of y equals to kx?
K.
Yes, that's right. And for the second part, for this diagram, it is a little bit difficult, but just like the Tina have just mentioned, y equals to k x with power 2. So what is the gradient of this one? Can you answer me?
2kx.
Yes, that's correct. So what's this mean? I think this is about the gradient of each point, because this is a curve. So they always so their gradients always changes. And for today, I'm going to talk about if there have many functions depend on more than one variables like f, x, y, and we want to know how the function changes when only one variable changes. And I'm going to talk about the example like temperature. It depends on multi variables like its position and maybe time. So can you give me another example like this? Yes, Victor.
Like, if you want to know how long the airplane will fly, you like depends on the weather.
Yeah, that's right. So the time of the flights maybe depends on the weather, the wind degree, or the temperature, or the flow speed. And next is the concept of the partial derivatives. We can look at this picture. It's just like a hill. And for this video, it shows that the x-axis and the y-axis, it's just like the north and the south of the direction of the hill. And why it can move down and up, that's because it changes from the z-axis. And when the z is changed, the x and y will change also. So you can see it can change just like a hill when it go up and down. And so this is the three-dimensional surface with arrows shows change in x direction and y direction. And when you change one variable, the others will also change. And the level curves. That means when the z is constant, there always have constant x and y. So now I'm going to introduce the formal definition of the partial derivatives. So about this sign, this means the partial. So the first line shows us the partial f, partial x equals to limit when h equals to 0. And for this function, our aims is to solve the problem when the x is changed. So h is the change value, and the next function just shows that x plus h, which means the x is changing and y keeps constant, and then minus the original function, and then divided by h. So y the limit is h equals to 0. That is because it is similar to the 2 dimensions graph. We always want to make the change as smaller as possible. So we can see that as a 0, and it's the same of the y, partial f, partial y. In this situation, we always keep the x constant and just change y, and then we can compare with the original function and then divide it by the change value h, which is equals to 0. So this is the basic formula of the partial derivatives. And next, I will give you an example. So we can see the question. That is, it gives us the fxy equals to x with power 3 plus x with power 2 and times y with power 3 minus 2 times y power 2. And this is a complex function with three changing variables. And I can show you the diagram of that. So this is the graph of this function. It is in irregular shape around the x-axis, y-axis, and z-axis. And the question asked me to solve the problem, which is to find the tangent plane, or you can find the point which has the gradient. So we can note that in the 2 dimensions diagram, the gradient of the point is a straight line, and in this graph, we can know that the gradient of this irregular shape is the tangent plane, just like a plane. And let's go back to the question. So the solution is, if we want to get the partial derivatives of x and y, we can just, when we solve about the x, just keep the y as a constant. And when we want to solve about the y, we just see the y, the x is constant. So the first part is the partial x, partial f, equals to 3x power with power 2 and plus 2 times x times y with power 3. That is because in this function, we always say that if we are solved with the partial derivatives of x, just see the y as a constant. So just give the derivatives of x, and then put down the power of 3 down, like here, and then minus 1. And keep the y with power 3 constants, and put a power 2 down, and minus 1. So, and then we can put the exact value, which is 2 and 1, into these parts. And then we get the final result of the partial derivatives of x. And it's the same for the y. We always see the x is constant and just change 1. And then put the point, which is 2 and 1, put into the functions, and we can get the final result. So here is some extended content. The first knowledge is the chain rule. The chain rule means if a function, just like this one, it have the x, y, and z, but it shows that there is another maybe variables, just like t. but it not appear in this function. So maybe the question will give us the connect with the t and x and the t with y. And so we always want to solve the problem with partial derivatives of x and y with the original f first, and then we can use a tree diagram that shows us firstly for this step it gives us the partial derivatives of x and y, and we can continue with get the derivatives of x with t and y with t, and then times them together, and these two parts can cancel, and we can get the final result of partial z partial t. And for the maximum and minimum value, if the f has a local maximum or minimum at a and b, and the first order partial derivatives of f exist here, then fx ab equals to 0 and fy ab equals to 0, and then we can get the local point. And if you want to know that whether it is maximum or minimum, it is a local or a point, we can use a test continually, which is to get partial derivatives again continually and take the test. In summary, partial derivatives are used when a function depends on more than one variables, and they measures how the function changes when only one variable changes, keeping the others constant. And through examples, we can see how they help us understand the real world examples like temperature and just like the time of the flight, just like the Victor mentioned. So this is the end of my presentation today. I hope you have a clear idea about the partial derivatives. So do you have any questions? Yes.
Back one slide. The chain rule.
Yeah.
I think maybe the chain rule, because it's implicit derivative.
Yes, it is similar to the one simple variables, and just like the tree diagram. Firstly, we get the equation between the z and two different variables x and y, and then there is no variable t in this function, right?
Yeah.
But we can get another two extra function like the x to t and the y to t, and so we can directly get the derivatives directly with these two and get the dx dt and the dy dt. Just like you said before, and when we get these two values, and we can put it here, and use chain rule to cancel out the partial derivatives of x, because we finally we want to get the partial derivatives of delta z and delta t, and we don't want to appear like x and y, only z and t. So we want to cancel out the x and y.
So if you do that things, you get the 2 df dt. So the final reason is 2 times df dt.
Actually not, because for this function, it have two variables, x and y. If you just keep this one, so what is the function of the x?
No, I mean, dx dt is different from dy dt.
Yeah.
Because they are two different implicit.
Yes.
But you want to cancel the dx and the zdx, dy and zdy.
Yes.
So you just leave the dt plus df dt. So the dt is different or the same?
The dt is different because they are in two different equations about the x and y. So dt is different.
Oh, okay, thank you.
Do you have any questions?
Okay, thank you.